But instead, I hope to sort of set up the common background for something called quantum graphs that I found interesting, and also hopefully it has to do with many talks this week about non-local games built around quantum sets, and also next week to some extent in the workshop. Yeah, and sorry. So I did prepare some materials, but anyhow, sorry. So if you have any question, of course, feel free to stop me, and I want to make it more bi-directional rather than just telling you what I prepared. So yeah, and so the overall plan is I'm going to explain some basic stuff today, and Sam Harris is going to talk a bit more tomorrow, I guess. And then, so after Sam's talk, maybe we take your input and think about how to continue. I mean, I might talk another day, or maybe we try to make some kind of open discussion day. But yeah, so that's the overall idea. So yeah, so do feel free to give your input. Anyhow, so let me start with some basic definitions about what these are, quantum graphs are. And so it came from several different fields of research. So there are many different viewpoints, and also in a way different goals. And so if you look at how to make sense of quantum graphs in the first place, there are actually two different ways to do that. The first way, or more like first ways, historical first ways, through something called operator systems that are some nice subspaces of space of linear operators on Hilbert spaces. So in a more quantum information theoretic context, it's due to Duran, Severini, and Pinter. And in more operator algebraic setting, it's due to Weaver. And in ages, so they define these quantum graphs as certain subspaces of metric space, or maybe a bit more generally for Weaver, the space of bounded operators on Hilbert space. Yes. I mean, this might look clearly if you are not familiar with infinite dimensional setting, but already with finite dimensional setting, so you have the space of matrices that's already rich enough. So if you want to stick to that, that's of course fine. And then, again, so in quantum information theoretic setting, there's not much. I mean, of course, you do have to assume that the S is self-adjoint, so closed under taking complex conjugate transpose, and also contains scalars. But that's it in a way. And in more operator algebraic setting, then so there is a bit more structure. So you want to assume some kind of consistency with given operator algebra inside BH. Anyhow, so I will try to explain something about this, what I mean by this consistency condition relative to algebra later. And particularly, Duran, Severini, and Pinter's goal was to make sense of something called confusability graph for quantum channels. So if you have a communication channel, then you want to look at what kind of inputs, which inputs could be confused after sending message to channel. And then you can draw a graph whose vertices are possible inputs. And you connect vertices when two inputs could be confused. So that means two inputs could give you same output. Then you get the graph called confusability graph of the channel. And they wanted to do something similar for quantum channels. So this was quantum information theoretic motivation. And for Weaver, I guess, so he was a bit more abstract-minded, and he wanted to make sense of possible structures on quantum sets that are modeled by these operator algebras. And once you try to think about relations on quantum sets, and then graphs are nice relations, so you arrive at this context, this concept again. Yeah.
Self-adjointness is supposed to be a kind of undirected.
Yeah, so you could say that.
In the operator theoretic perspective, has anybody looked at the not like a sort of directed version? Or?
Yes, yeah. So I mean, you can drop this self-adjointness, and like you say, so you get like a more general relation corresponding to like direct graphs. Yeah. So I think, so in Weaver's paper, he really thought that or defined like hierarchy of conditions you can put on quantum relations. Okay, so this was the like historically first perspective on quantum graphs, but today I want to explain you a bit more newer approach due to Musto, Ruiter, and Verdon. That is, in a way, more hands-on, and it's easy to produce more examples, I think. And of course, this is great. And particularly if you start from like quantum channels, of course, you can define the confusability graph in this way. But if you really try to cook up quantum graphs on its own, then so this viewpoint is very useful. Again, well, the starting point is quantum set modeled by certain algebra of operators, or maybe a bit more abstractly, C-star algebras. But then you want to think about how to model map between such quantum sets. And then, so in more sort of categorical viewpoint, so you can do some diagrammatic calculation inspired by tensor network. And well, through that, you can make sense of adjacency matrices for graphs in this quantum set framework. So the first approach gives you something like sort of functions on the edge set of the graph, morally. And so this one really gives you adjacency matrix. So for example, if you want to talk about properties of graphs, then having concrete linear map to talk about eigenvalues or whatnot. So that's very convenient, of course. And also, if you want to talk about maybe something like generalization of what you can do with usual operator algebras into a bit more categorical viewpoint, like tensor categorical setting, then this is very like good to start with. So I think so there are some recent development in that direction, like going beyond usual operator algebras and going more into sort of higher structures like tensor categories. To these. Okay, so that's the, and I want to start my, sort of build my talk on the second viewpoint. And then let me explain how to make sense of these quantum sets, and that's sort of suitable for this adjacency operator. And well, to make it concrete, I want to just work with finite quantum sets that are modeled by finite dimensional algebras. I mean, to make it concrete and to not to care about analytic subtleties. So what are finite quantum sets? You want to consider finite dimensional C-star algebras. In other words, just multi-matrix algebras. On its own, this is very simple. You have a bunch of matrix blocks and take direct product as algebra. There are n direct summands. But, well, if you know the sort of yoga of non-commutative geometry, maybe, then so you think of these non-commutative algebras as something like function space on quantized sets. But as it happens, this alone is not very, not quite enough to make sense of quantum graphs. So we need to give some kind of measure on quantum sets. So this is another structure. And being an analog of measure, so you want positivity. So what do I mean by that? So if you have these matrices with complex components, then you can always look at the positive semi-definiteness of matrices. And for such positive semi-definite matrices, you want non-negative numbers. And faithfulness, so that's if you have non-zero element, non-zero positive semi-definite matrix, then you get non-zero number. So psi of A star A. So that should be positive if A is non-zero. Okay? And of course, if A is zero by linearity, you get zero. So this gives you some kind of measurement scheme if you are quantum information minded. For example, you can take usual trace function of matrix algebra if there's just one summand. So that's a good choice. And instead, if all matrix blocks are size 1, then this is just a function algebra on some finite set. And then this corresponds to a genuine measure on the finite set. Okay? All right, and formally, out of such faithful positive functional psi, we can create a Hilbert space whose underlying vector space is B, but you can define inner product using this psi. That's called the Gelfand-Nymark-Ziegler construction. Let me write it like L2 space, but as a vector space, it's just B. So how do I make sense of the inner product? If I have two vectors, and let me use physicist convention. So the inner product is linear in the second variable, conjugate linear in the first variable, and just use this. And one of the miracle is this simple formula is really well-defined inner product. Of course, block by block, what you are getting is something like Hilbert-Schmidt inner product of matrices. And well, if size a trace, it's really that. In general, there's a bit more complicated structure, but still, this is a well-defined inner product. And we get a finite dimensional Hilbert space. Okay. But then, so their insight was, so once you have this Hilbert space structure, actually the quantum set B and psi start to have more structure. I mean, not just algebra and functional, but there is something called Frobenius algebra structure on this B that you can start doing some nice stuff.
Classical sets already kind of can be included as just one.
Yes.
Decay is one.
Yeah, so ODK is one, corresponds to commutative algebra of sort of pointwise product of functions on finite set.
But already you're introducing the classical ones, you're introducing this extra data.
Yes, yeah. So I want measure to be there.
So classical usual set is not really.
Yes, maybe you might want to object that. And of course, so there's always a canonical choice of psi.
Sure.
And so maybe, yeah, anyhow, it's good to write the canonical choice. So the standard choice is, it looks a bit weird, but you take this dk times trace of mdk. So this is actually the nicest choice, corresponds to something called delta form. Well, yeah, anyhow. So yeah, in a way, I mean, so you can make the convention that you always take this choice. And that corresponds to, no, yeah, so that's the really ordinal trace, so sum of diagonals. But then I even amplify that with tiles of matrix. So.
Sometimes called the Markov.
Yeah, or branch-level state also. I honestly don't know what the like good convention is.
Special delta form is okay.
Yeah. Okay, so what do I get out of this? So being an algebra, B is an algebra, so I have a product map. Call it M, but let's say because this Hilbert space is identified with B as a vector space, let's think of it as a map acting on these Hilbert spaces. But anyhow, it's just this, sorry, product. And also, there is a embedding of the unit. Say alpha goes to alpha and b. Call it eta. Okay. But then using the Hilbert space structure, so these are all Hilbert spaces. So I can take the adjoint of these linear maps. So that's the extra thing you can do. For example, the adjoint of M, that's a map from L to B to the tensor square. And adjoint of eta, that's map from A to B to C. Okay. But so the second one, so that's actually easy map. I mean, if you just unpack what we are doing, the eta star is actually just take the psi functional. So this is actually psi. But anyhow, the adjoint product, this is more non-trivial. And usually we call it the co-product. And call this co-unit. Okay. And well, so there are some consistency conditions between product and unit. For example, so if you, sorry, let me introduce a diagrammatic way to denote these maps, motivated by tensor network calculus. So I'm reading from bottom to top. So this B sort of next, well, two copies of B represents B tensor B, single B, B itself, and so this is my product map, diagrammatic presentation of product map. And similarly, for this one, in the tensor network calculus, the complex number space, I mean C, is like empty node. So from C to B, so this is my eta. I mean, this circle represents something like empty node. And then the co-product is going the other way, from B to B tensor B, and eta star goes like this. Okay? And what are the consistency conditions between M and eta? So if you compose sort of M and eta, that means stick this diagram into one of these inputs, then you get identity. So that's the one times something is something, okay? And associativity of M means if you compose M twice, so for example, if you compose like this, this is equal to the other composition like this. So that's the associativity of M. And the compatibility with unit and product means if you take composition of product and unit, then you get identity of B, and similarly in the other way, okay? So this is my identity. And of course, for M star and E star star, so you get this same kind of consistency condition just by flipping the diagram. But so this is still not interesting. I mean, you just take what you already know and take the adjoint, so you keep the same kind of relation. What's interesting is when you start to mix this M and the adjoint, then so that's a new kind of structure. So maybe I should just. So what do I get? So if I compose M and M star, then, for example, I can do this. So that means take M star here, tensor product with identity of B, and here it's identity of B tensor product M, and compose in this way. So in the middle, you have triple tensor product of B, right? But start with just tensor square of B and end up with, again, tensor square of B. And if you do this, there's another composite of product and coproduct, much easier, like this. So this one M and M star. And as it happens, these are equal. So this is like really non-trivial thing. You can have, although I mean it's true with what I said, take any finite dimensional C-star algebra and positive functional and define a coproduct this way, coordinate this way. I mean, so this one doesn't have to do with coordinate, but anyhow, we get this. And then another thing, nice thing, is the right-hand side is obviously self-adjoint. So you can take the adjoint of the left-hand side and have the equality also. And the adjoint becomes something similar, but it's the other composite like this. And that's the Frobenius algebra condition. Okay, so out of this, you can do actually quite a lot. So in a way, as long as you have some kind of tensor network-like system with this condition, then you can reproduce quite a lot of what I say today. Okay, then finally, I can introduce the adjacency matrix operator on such quantum sets. Yeah, I'm afraid I sometimes say adjacency matrix, sometimes just adjacency operator, but anyhow, you know what I mean. So this is an analog of adjacency matrix for finite graphs. And it's going to be a linear operator on B, or maybe GNS space of B. And just to emphasize that I have a structure of Hilbert space on this finite dimensional linear space, I write B borrowed from theory of infinite dimensional Hilbert space, but there's nothing about boundedness. I mean, so this is finite dimensional space. But the important point is I can talk about adjoints of elements in this linear transform space. So that's the only thing. Okay, and what's my consistency condition? The important one is if I compose A with product and coproduct. So what's this? So this is you first do M star, so start from B and then go to B tensor B and then apply A on both components. Then take product M again. So overall, it's a linear map from B to itself. And this should be equal to actually just A. And also, so there are other ways to compose like this. So again, M star here, M here, and I mean, so it's a composite of M star identity, M star tensor identity, then identity A identity, and then identity M. Okay? Oh, sorry, no. I need to close this. So here's my eta and eta star. And this one should be equal to A. And finally, A should be actually self-adjoint. So what does it say? The first equality says A should be idempotent for a new kind of product operation that corresponds to sure product of matrices. I mean, it's the dumb product. Take the component-wise product of matrices that you tell not to do to students in linear algebra course, but now I'm doing that. And then what's the second equality? Second equality says A is something like symmetric matrix. So if you do this, morally, so this is like changing output to input and input to output. So this is like transpose of matrix. And the last condition, or maybe A equals A star, that's of course self-adjointness. And if you have self-adjoint symmetric matrix, this is like real matrix. And also, I mean, For classical case, it's a bit redundant. I mean, so this one already foresees that the components are 0 or 1. But anyhow, so this says some kind of sure product idempotent condition. Okay. Anyhow, of course, in the quantized case, the first condition doesn't quite force that the A is a matrix of zeros and ones. So we have to add these conditions. But anyhow, I mean, so this is some sensible condition we can ask for linear maps. And there's another normalization condition that's not as important, but anyhow, convenient to have. If you take this composite just with one copy of A, then we can ask that it's actually identity. Or in other words, convolution product of A and identity should be identity. But this is just a normalization condition that corresponds to your graph having one loop at each vertex. Or I mean, the adjacency matrix has ones in the diagonal. So it's just a convenient normalization condition you can add or remove. For example, usually for like usual approach to graphs, you don't want these loops at vertices. So instead, you assume that you have zeros on the diagonal. That corresponds to this being 0. So it's something, I mean, that's another sensible convention. So. Okay. And yeah, if you want to recover a classical graph, then what you do is to take the commutative C-star algebra. So that means all the matrix blocks have size 1. Sorry. And then as functional, take that standard functional. That means just the sum of components. Then you really recover classical notion of adjacency matrix. Why? So if you unpack the M star in that case, it's just something like send each delta function at a point to its tensor square. So that's what the coproduct is doing. Then the sort of convolution product of operators, that's really sure product in the usual sense. So you recover the the first condition, A convolved itself equals A. So that really recovers that the components are zeros or ones. Then the second equality says A should be symmetric. So you get the symmetric matrix of zeros and ones. And that's adjacency matrix for undirected graph. And then, yeah, like I said, so this is just a normalization condition. Okay, but of course the really interesting case is when you have non-commutative algebra, and if you have just one matrix block, then that more or less corresponds to the setting of Duan-Severini meter. And yeah, so I guess the other case is it's a special case of Weaver's testing. Anyhow, so this is the classical example, just a sanity check that you are really generalizing the classical theory. But of course, so there is a quick, fast example. Like I said, as long as these diagrammatic calculus make sense, then you can play this game. And in particular, you start with such classical structure with some kind of symmetry. For example, if your vertex set has a structure of commutative group, then you can look at the equivariant maps for the commutative group structure. So that means, for example, what's a equivariant graph? So that's a Cayley graph of a group. So you fix a say you fix some subset in a group, and then you say two vertices are connected when the difference is in that prescribed subset. So, and if you do that, then everything sort of translates to tensor categorical deformation, and you can do something called two cocycle deformation. So let me spread that. So if gamma is a finite commutative group, to be precise, and start with a subset of gamma, so it may be, to be precise, x is equal to its inverse. Connect the G and H, if and only if G H inverse is in X. So you get a graph, or maybe quantum graph, whose algebra is the function algebra of gamma. Okay, but what I can do is to use the group structure and think of it as a group algebra of another group, namely the Pontryagin dual group. I mean, now we have finite commutative group, so the dual group is again isomorphic to gamma. But anyhow, we can do that. So this is the baby version of Fourier transform. And as a group, it's another, I mean, it's isomorphic to gamma. Okay, but then what I can do is to start to deform this algebra. And so if you have something called two cocycle gamma hat, so that's a consistent way to deform a product in the group ring into another associative product, then we get a non-commutative algebra as the result of deformation. So For example, I mean, the archetypical example in quantum information is to take the Klein-4 group, so Z2 plus Z2, and then there's a non-trivial two-core cycle. If you do this deformation, you get the algebra generated by pilot matrices, so four-dimensional non-commutative algebra, namely M2. And yeah, so the great thing is you can just take the same adjacency matrix operator on this as a linear space. I mean, you can always identify this with the twisted group algebra, and the really same operator works. So for the K graph. Okay. And I mean, so this kind of flexibility is what's really powerful about the second viewpoint, I think. I don't know, maybe shall we take a quick break? Or yeah, in a way, I mean, so, this is really the first definition and first example. So maybe if you have some question about this, good time to ask.
Explain how the Duran-Severin event structure is recovered in this framework again? You just have one.
Yeah, good point. So this is actually something I was going to talk next.
Oh.
So maybe yeah, let's continue into that and take another possible break. Yeah. I mean, so if you try to look at the original formulation of quantum graphs, I mean, so this is not so obvious how they should correspond.
More questions?
Yeah, maybe yes. Other questions about so far?
This last example where you don't assume that gamma is fugitive?
Yeah, then another good point. So you can start from gamma hat, and then as long as you have adjacency matrix operator on the group algebra, you can still do this. But of course, then you start to lose the original starting point. So you have to start from some non-commutative group that's going to be in gamma hat.
Okay, so we don't have any more. Do you want to have a 5-minute break, or I don't know?
Well, yeah. Let me just explain the next thing, and then let's take a break. Yeah, yes. I mean, it's going to tie the two viewpoints together. So it's nice to sort of nice quick closure for the first part. The yeah. So what can I do? So if you have a adjacency matrix operator in the same set, so basically the most important condition is the convolution idempotent. So A then I can define a subspace of the space of linear operators acting on the L2B. How do I do that? Just by take this convolution product of my A with any other linear transform. So formally, this is a subspace of this. Right? Start from B and end up in B, and factor through B tensor B in the middle. And well, out of the defining conditions for the adjacency matrix operator, we can quickly see that its self-adjoint contains scalars. Well, so why is that? And by the way, so if you are not familiar with the terminology, operator system is by definition a subspace of the space of linear transforms on Hilbert space with two properties: being closed under self-adjoint, being closed under taking adjoint, and contains scalars. Oops. So why do we have the first condition? Let's take the adjoint of this formally, M star and M, so they just get swapped each other. And in the middle, I end up with A star and T star, right? But our standing assumption was A is self-adjoint. So this is just A convert with T star. So nothing fancy. And as for the second condition, this is where the normalization matters. I mean, so my normalization was that if you convolve A with scalar, then you get scalar. So that's making sure. Yeah, and so not quite direct at the defining conditions. But there are some other nice things. And if you really exploit the other conditions, then we can check that the SA is invariant under conjugation by something called modular operator. That you don't care if the function has such race. But in general, it's something a bit non-trivial. And yeah, anyhow, so I guess if you want to know about that story, I guess we'd better do that later in the week, not today.
So not every operator system arises in that way.
Yeah, good point. Yeah, so there's yet another point. So maybe I should spread that. So if you look at what the T would be, I mean, T is spanned by rank 1 operators. And if you unpack what these, or maybe, but let me put it that. So in general, you have so these functionals on L2B and vectors in L2B, and you want to take linear span of these, insert in T. And so if you look at the diagrams like this, you see that there's a right multiplication by B here. And here, I can do bending around. And this is, again, A and something like this. And so there's a right multiplication twice, before and after A. So there is definitely something with the B. And spelling this out, so C is just another vector such that this part is actually this part that you get by Frobenius condition also. So actually, we see that the SA is of this form. What I mean by this, B prime, it's the commutant of B acting on L2B. And well, so my convention is B acts on itself by left multiplication. If you look at the commutant, so that's something that commutes with this left multiplication, it's the right multiplication. So B prime, it's a really set of right multiplication operators. A goes to AB. And yeah, I mean, so we really have this. It is a particular operator system that's closed by these right multiplication actions from both sides. So this is exactly Weaver's condition. So besides being an operator system, you want this bimodule property for the commutant. Okay, and another observation you can do is so the defining elements of SA, so A composed with T. So this is result of some orthogonal projection. So T goes to this AT convolution. So it's just an orthogonal projection from this B L2B to SA. Of course, then I need to specify the inner product on this metric space. It's not quite the Hilbert-Schmidt inner product, but something very close. Again, I mean, I need to define an inner product of two linear transforms on B. How do I do that? So if it's a Hilbert-Schmidt inner product, I should compute T1 adjoint times T2, take that trace, right? But then I want to do that in a bit more sort of diagrammatic fashion. Then I get M and M star sandwiching this up to identity, then take unit coordinate, close the diagram. So it does depend on the structure of original B, but anyhow, it's again inner product, very defined inner product on this B of L2B. And yeah, I mean, so just work at division. And actually that map, I mean, it's obvious that it's idempotent operation because A is a convolution idempotent. So if you do this twice, it's the same thing as just doing it just once. But a bit more importantly, it respects this inner product, and it is really the orthogonal projection. So for example, A itself, it's the image of the rank 1 map, like this, under this orthogonal projection and all that. So you can derive quite a lot again about the operator system structure of SA from this interpretation. Yeah, like I said, for example, to see that it's conjugation invariant for the modular operator, this is one way to go. And another proof is in Matthew's lecture note, Matthew's note. But anyhow, one way or another, you get that the SA is not just a operator system, but first of all, it has to be bimodule for the commutant, and also it has to be invariant under modular operator, I mean conjugation by modular operator. These two the extra conditions you can have.
You have a trace.
Yeah.
What does this condition look like?
Sorry, this one? Then I mean still this one, it's a non-trivial extra condition. The modular operator doesn't matter. But yeah, so even if you have, even if the psi is trace, so this is extra assumption.
Okay, I take divided matrices.
Yeah.
I take some operator system,
Yeah.
and then
So it's a linear span. Sorry. So I meant it's not just a simple product, but take the linear span of such. Yeah. So I guess the easy stuff like taking sums absorbed by this linear span.
but there is a way to reconstruct A from SA, right? There is
Yes, yeah, like really, A is the image of this for the orthogonal projection. So I guess that's the quickest way to recognize A.
Go back to the confusability kind of graph.
Yes.
Is there some kind of special property of the quantum channel that, because I mean, if you have so any operator system will be the confusability
Yes, yes. So,
of some.
yeah,
So
yeah.
this one is special.
Well, so actually, again, if psi are traces, any quantum graph is a confusability graph for some CP map, UCP map.
For sure, because every operator system. So yours.
Yes, but so the important point is you want to implement this as a UCP map between C star algebras, and then I mean, of course, if you embed your C star algebra into some big matrix algebra, then by what you said, you can always find some channels acting on these matrix algebras. But if you want UCP map, say, on C star finite dimension C star algebras, then there's extra bookkeeping you have to do. But it is still through, yeah. So that actually, so I am preparing that with Matthew about that. I mean, it's a very short, quick project, but anyhow, you can recognize any quantum graph as kind of confusability graph for quantum channels acting on these C star algebras. Yeah, again, I guess if you want to know more about that, maybe we'd better do it later in the week. But for finite dimension C star algebras, it's really take what you improved for matrix algebras and do necessary bookkeeping. But anyhow, it's something nice to know, I think. Okay, any questions about this? Yeah, if not, then maybe shall we take like, I don't know, yeah, 10 minutes break or whatever. Yeah, yeah, let's say 10 minutes. yeah, in the first place, like how long do we want to continue? I guess that's the right question. And yeah, okay, let's say we could continue a bit more. And yeah, anyhow, in any case, I don't want to like talk about everything, of course, and yeah. So let's see like what you want to continue with tomorrow after some talk, and yeah, maybe something more, or maybe you get fed up and quit already. Anyhow, right? Sorry. So that's the basics around like how to formulate quantum graphs and how different viewpoints come together. Yeah, by the way, maybe good time to take a quick roll. So do you want to hear something a bit more in the direction of non-local games, or something more representation theoretic and quantum groupy stuff? I mean, like who would be more for tensor categories? Maybe not. Yeah, I don't know. Yeah, in any case, they converge in the end. So, yeah, or who would be more for non-local game stuff? Okay, yeah, so shall be. Right, then let me talk about the something a bit closer to these non-local games, although not quite, because I guess we are going to hear more from Lidomira and Ivan and Jason on Thursday, but just my perspective. Once you have graphs, you can talk about homomorphisms of graphs or isomorphisms of graphs. And as it happens, these are quite interesting and leads to interesting algebras that are sometimes infinite dimensional, even you start with finite dimensional structures. So let's say you have two quantum graphs, G1, that's given by, say, finite dimensional algebra B1, and space for positive functional psi1, and identity matrix operator A1, and similarly G2. Then we can think of what it means to have a quantum homomorphism. And well, long story short, one way to model that is to look at certain homomorphism from one of these algebras, say B2 to B1 tensored with another algebra. I mean, of course, the obvious way to think about that is just to look at homomorphism between these B1 and B2, and with some kind of consistency with the structures. That's valid, but not quite interesting enough. And if you start to put some kind of auxiliary coefficient or ambient system, that's interesting. Yeah. First of all, we want another C-star algebra. I mean, for my taste, I'd like infinite dimensional C-star algebra possibly, but if you don't like that, just C-star algebra of arbitrary size, finite dimensional C-star algebra but of arbitrary size. That's already interesting, I guess. And like I said, homomorphism. From, let's say, B2 to B1 tensor C. So when we talk about homomorphism from G1 to G2, I want to sort of flip the order of indexes and talk about something like from B2 to B1. That's because, so they represent something like functions on vertex set of the graphs. And if you have a map between these vertex sets on function space, it's the other way. But important thing is you have something like ambient system C.
What does it mean, star homomorphism?
Yeah, star homomorphism, of course. Yeah. I mean, I'm again being sloppy. So if I have a map of C-star algebras, that's map in very good conceivable sense. Yeah, but good to be precise. Thank you. Right. Anyhow, that's that. And oh, sorry. Of course, with consistency condition with A1, A2, so on. And what do I mean by that? First, so this might look a bit spooky, but let me make it a bit more symmetric. I mean, the way, sorry, let's call it theta. And theta is by definition homomorphism from finite dimensional C-star algebra into another big one. But let's make it a bit more symmetric. And make it a map between these two tensor products. But so it's going to be more symmetric, but the price I need to pay is this is not the homomorphism anymore. I want to send B tensor C into this theta B. That's an element in this tensor product. And then take product with this. So if you know the language of Hilbert modules, this is a map of Hilbert C modules. I mean, it's obviously C module homomorphism. So C is acting from right by multiplication, and yeah, I mean, it's just giving C module homomorphism. The right C module homomorphism. Okay, and in terms of theta twiddle, this should satisfy. So one thing I can do is start taking the adjoint of this linear map. I mean, for homomorphisms, taking adjoints don't really make good sense. But if I turn that into a map of right C module homomorphisms, then the adjoint makes sense. And I will spell the precise definition, but take my word. And then what's the theta twiddle doing is just, it's a linear map from this to this, right? And then SA1, that's a subspace of linear maps acting on B1. So I can take the composition of these linear maps and then come back to original B2 tensor C by the adjoint of theta twiddle adjoint. Overall, it's a linear map acting on B2 tensor C, and I want this linear span to be inside SA2 tensor right action of C. Okay, so this might look a bit strange, but in the end, it's a kind of consistency condition with this original star homomorphism and these operator systems.
does it imply some commutativity with A?
Yeah, so that I really would like. So for the quantum isomorphisms that comes next, you can have that. For this one, I don't quite know. I mean, maybe it is, but maybe that's a bit too much to ask. Okay, so that's a quantum homomorphism. Yes, yeah. So it's one quantum homomorphism is given by such data. Yeah. So.
Position of homomorphism?
Yeah, good point. So that makes sense quite well. So if you have 3 quantum graphs and 2 homomorphisms like that, maybe actually it's a good point. So if you have, say, G1, G2, G3, quantum graphs, and so those data, so that means I guess I want map going like this. So B3 goes to B2 tensor D, and then B2 goes to B1 tensor C. Then, sorry, I can compose these two as a map from B3 into B1 tensor, let me do it carefully, B1 tensor C tensor D. Well, I mean, you first use this, right? And then act by this map in the B2 factor and end up in this big tensor product. So the composite of 2 quantum homomorphisms is represented by C tensor D in place of C and this composite homomorphism. And of course, you need to check that this consistency condition is good, but it's a just exercise.
Are you assuming that the C and D are finite dimensional?
No. So I'm not. So this makes sense. Sorry?
Do we take the minimal tensor?
Yeah, but I mean, so the B1 is finite dimensional, so you can take minimal or maximal, so they agree.
If you compose, then you get tensor.
Oh, good point. So here, I guess there's a bit of choice, and maybe so the good convention is I just take max, although min also makes sense. I mean.
So because we're taking the adjoint theta tilde star using the Hilbert C-star module,
Yeah.
there's no obvious dependence on the states psi 1 and psi 2. Is that correct?
Well, so there is because yeah, so this is one thing I didn't really say, but Hilbert C module structure comes with C valued inner product. So you need to make sense of inner product, this value in C, and then you need some scalar inner product on B2 or B1. So that comes from psi 1, psi 2.
Automatically, in this context, that the adjoint to theta tensor exists.
Yeah. I mean, so because I mean, you can really write it out. So in the end, the theta twiddle looks like sum of sorry, I mean something like bi b prime I star tensor ci, I guess, as a map of Hilbert modules, and then you can just formally take adjoint of this expression. So that's adjoint. So theta twiddle.
This is B1 and B2 are finite dimensional.
Yeah. So I can really work with finite sum here. So now and then, that helps.
the actual in terms of height.
Yes, yes, as maps on Hilbert modules and take the, I mean, so you want to check that this is adjointable with this exactly the adjoint. And okay. And then so this was quantum homomorphism and composition. And by the way, maybe something stupid, but still nice to have. What's the identity map on quantum graph? It should be given by identity map of algebra. And then C is going to be just the scalar algebra. And you take theta to be the identity map of the same finite dimensional C-star algebra, and it sort of checks out. Okay. And so what are the quantum isomorphisms? Of course, you want, yeah, I'm hiding what I wrote there. I want quantum homomorphism in this sense, with some kind of invertibility. But of course, it's not easy to make sense of the inverse of theta, because I mean, there's no way to directly make sense of the inverse of theta as a homomorphism from B1 to B2 tensor something, right? So I need to do something a bit different. So then what do I want? So instead of asking for an inverse map, I want compatibility with the Frobenius algebra structure I had. So for example, psi1 tensor identity of C hitting on this. That should be just psi2b times 1. So this is one of the compatibility, okay? And if I act by M star, so this is the action of counit, by the way. That's the counit. If I act by the coproduct, then I should end up in B1 tensor C. And I want that to be something coming from like coproduct of B2. That gives me something being B2 tensor B2, and then action of theta. Then the right thing to do is theta 1, 3, theta 2, 3, and 3b. So I guess the right-hand side needs a bit of unpacking. So like I said, so this one lives in B2 tensor B2, okay? Then if I hit elements in this tensor square by theta on both factors, I get something in B1 tensor C from both factors. So, but I only want one component in C. Then I should be taking product in the C part, but don't touch the B1 part. So this way, I get a well-defined element in B1 tensor B1 tensor C. Right? So that's what this is to represent. Okay, and sorry, yet another thing. Again, so if I do sandwiching of this operator system by theta twiddle adjoint, SA1. Then they should just conjugate this operator system in this sense. Again, I mean, it seems a bit lame because here I had something like this, finite dimensional operator system to start with. Here I need to take SA tensor C. So I don't know, maybe there's a clever extra argument to reduce to something like just conjugation by theta twiddle in the other way and just reduce to more symmetric condition. But so this one, I honestly don't know how to. Anyhow, so this is one convention of quantum isomorphism. And if the coefficient algebra C is just scalars, then you really recover automorphism in the usual sense. That means these two conditions here really implies invertibility of a map. So that's, again, not so obvious, but it's the power of Frobenius algebra giving you this. So I think in algebra, so if you have finite dimensional Frobenius algebra and compatible map in this sense, it becomes invertible automatically.
And if you start from classical graphs, you
Yeah.
get the notion of quantum isomorphism.
Yeah, so even for classical graphs, if you have quantum homomorphisms or quantum isomorphisms in this sense, then so there are more.
So are they compatible with these notions coming from non-local games?
Yes, yeah. I mean, so you, this is more or less the modeled on this non-local quantum isomorphism game. Yeah. So maybe the important point is so this implies this commutativity with adjacency metrics. So this one, again, to be very precise, so there's an implication from this, so A1 tensor identity theta. So if you ask for this consistency condition, you get that. The other way, if the two quantum graphs are already the same, and if we are talking about something called a compact quantum group that I want to mention a bit, then there's a reverse implication. And again, maybe so there's some trick to do it in this more general setting, but that I don't know. So I guess this is really the consistency with adjacency metrics in the classical picture. Okay. For example, if you do two co-cycle deformation of Cayley graph for commutative group, then so they become quantum isomorphic in this sense. And I guess so in that case, the C algebra is, maybe it's better to spell it out. Commutative group gamma and some subset inside X. So that gave you a Cayley graph, right? And if you do the two co-cycle deformation of this group algebra of the dual group, then you got a quantum graph. omega gamma hat. And in this case, well, so this happens to be quantum isomorphic in that above sense, and this is my Cayley graph is G, and this is my G omega, and G is isomorphic to G omega by, and then I need to give you a homomorphism from, say, B to B omega tensor something. And also, one thing you can do is take the opposite to Go cycle, or I mean conjugate to Go cycle, and do the obvious thing, namely send group elements to group element itself, tensor itself, but in this twisted algebra and twisted algebra for the composite conjugate cocycle. So gamma goes to gamma. And of course, these factors have no non-trivial product rule, but if you take omega and its conjugate cocycle, then on these elements, they cancel out, and you get a copy of original group algebra. So this is the argument to see quantum isomorphism. But of course, so I guess there are other ways to see that they are quantum isomorphic.
I start with the Cayley graph and say I have a quantum isomorphic monograph. Do I know that it always arrives in this way, or?
That may be no. I mean, so this one definitely has more structure than general case. So, but yeah, I mean, many interesting examples already show up in this way, I guess, by two-cocycle deformation. But well, for example, I mean, like I said, as long as you can do tensor categorical phrasing of diagrammatic calculus, you are good. And then so there are something called monoidal equivalent groups. So you can have defined groups that that have the same representation category. So once you have that kind of setting, then you can possibly go out of this two-cocycle deformation.
So can you say again? So is this a statement that whenever I have two monoidal equivalent finite quantum groups?
Yeah, then, well, of course, so I sort of lied a bit. So we need to have adjacency matrix in the representation category, but that you can do with the language of Frobenius algebra and all that. And then, yeah, I mean, so this is all placed in tensor categorical language. So it's independent of the choice of fiber functor, and yeah, it should be, but hang on. Yeah, so I might have to take it back. If you want like really implementation of quantum isomorphism in this sense, I guess there's a bit of consistency, not just like choice of different fiber functors. Yeah. Right, and okay, then so this is how to make sense of quantum isomorphisms, and a quick example. So for example, by this, you can see that the if you take the Klein for group and do the two-cocycle deformation into M2, then you can start to see like some Cayley graphs on the Klein group should be quantum isomorphic to some operator systems inside M2. And that are not too difficult to classify. So okay. And I guess, so this is sort of worked out by Matsuda in the generality I'm talking. So he classified quantum graphs on M2 with possibly non-trivial weights, so non-trivial functionals. Okay, and there's one important observation. So, so we had this Hilbert module structure on this B1 tensor C or B2 tensor C. And with this consistency with Frobenius algebra structure, actually theta twiddle ends up being isomorphism of Hilbert modules. In other words, the adjoint ends up being the inverse map. So that's again a very useful thing to exploit. Okay, then let me quickly explain the algebras that have to do with the universal presentation of non-local games for quantum isomorphism problem of such quantum graphs.
Is there inverse homomorphism at least? Did you ever mention
No, I mean, still, yeah. At least there's a candidate, approximation in a way. If the sites are traces, if sites are traces, then the M star ends up being a star homomorphism again. I mean, this one literally. So if you take the adjoint of this equality, then you get something about M and theta twiddle stars. I mean, interpret this as something about theta twiddles, and take the adjoint. Then it says that the theta twiddle star is a homomorphism from B1 to B2 tensor C, I think. But it's not a star homomorphism in general. So that's the. But if the sites are traces, it is, and that's the closest you can have to inverse, I think. Otherwise, no. But yes. Yeah. So again, I mean, so this is something. I mean, you keep these consistency conditions obviously, and again, so this is formulated in the way you can have. But of course, I mean, so the thing is, if you try to make sense of the inverse as something like theta twiddle star restricted to B1, then you still end up being something like this for the composite of theta and theta star. So you don't quite have usual inverse relation. It just says there's enough matrix coefficients for the composite map to recover something like identity map. And actually, so the next thing sort of makes it precise. Oh, sorry, do I want to? Yes. So let me try to wrap up today with one extra thing. So I guess, so formally speaking, if you do non-local games built around these structures, then the algebra C and some functional on C will give you a quantum winning strategy for the non-local game of quantum isomorphisms. But anyhow, so that we will hear on Thursday more, I guess. And for the moment, let me explain a bit of abstract algebra approach to understand the universal structure behind these quantum isomorphisms. So let's look at all possible solutions to our problem. So C and theta and with the compatibility condition, like I said. Then, in the end, so there are, of course, there's going to be infinitely many of them, but in the end, the structure is kind of controlled by what happens to the B2 and B1. What do I mean by that? So theta itself is a homomorphism from B2 to B1 tensor C. So in a way, you can look at the matrix coefficients. So look at what the effect of theta is on, say, basis of B2, and that's going to be sum of simple tensors, say, basis in B1 times some element in the algebra C. So if you look at these sort of expansion in terms of basis, then you get some kind of matrix coefficients of theta in the algebra C1, in the algebra C. So you look at all possible sort of possibilities and the algebraic relations among them, then you can make sense of the universal algebra of such structures. And B2. So what I mean is this is some kind of some algebra whose concrete representations to Hilbert spaces give you solutions to this other problem of finding C. And then so so there is something corresponding to theta as well. I mean, it might look scary, but in the end, you just look at all possible solutions to C and say that it's the abstract star algebra controlling C.
Because B1 and B2 are finite dimensional, you can just write generators and relations, right? It's
Yeah.
horrible,
But then, so as for relations, there's no control. I mean, the only thing you can say is relations that are valid in any C. So that's what I mean here. So you sort of expand. So there's Bi is a basis in B2, and B prime J is the basis in B1, and then Cji, that's an element in C, right? And you just look at these elements, look at the relations they satisfy, and then, I mean, you just want to keep relations that are valid in all choices of C. So that's what's defining this universal algebra. So, yeah, there's nothing finite about the number of relations. Yeah.
Kind of the definition of this star algebra written down somewhere?
I just for the cases without adjacency graph, I guess, in one of paper by Mike and Sam, yeah.
Over, yeah.
With adjacency matrix, I'm not sure. I mean, but I guess you can take this as the definition. I mean, what I said as a definition, I think. Yeah. Sorry. So I actually prepared a lecture note based on a graduate course I gave in the spring in Oslo, and I wanted to make it available to you. So I was too lazy to like fill up the details, but I guess I can make it available to the program participants. Yeah, to the. Yeah. Okay. And hopefully it's a bit more complete than this, but still, yeah. I mean, I don't think there's any like finite set of relations you can always make sense. And for beta was that's the richness of the structure. So, for example, because the relation could be so few, the algebra you define this could be infinite dimensional. That means there are infinite dimensional C-star algebras possibly. So even if you start with finite quantum graphs. And actually, it doesn't matter how complicated your graph is. More like the more complicated your graph is, so the smaller this is going to be, because you have less isomorphisms. So, for example, if the graphs are trivial, like empty or complete graph, then so this tends to be bigger. So I guess I better wrap up soon.
Maybe just to clarify, so G1 and G2 are classical.
No, quantum graphs given by B1, Psi1.
Yeah, but
yeah.
if they came
Yeah,
classical,
yeah.
then this is what we all already know.
Yeah. So if there are classical graphs, then it's like really spelled out, like how to define the Yes, so yeah, somehow, so the annoying thing is, so this condition with the operator space is a bit difficult to like really say precisely in quantum graph case, but for classical graph, you can just replace this into condition about adjacency matrix and theta sort of commuting.
What if just one graph is classical?
Still, not that I know. Okay, so let me wrap up with just one extra thing. We can talk about automorphisms in this setting. I mean, just take G1 and G2 to be the same. Then we are talking about, I mean, of course, the G is isomorphic to itself, but we are talking about like possible quantum strategies to convince referee by possibly like really not working with genuine automorphism of the graph, but something like just partially defined thing. And we defined these through the idea of quantum isomorphisms, but this one ends up having a nice quantum group structure.
You wanted to say G1 equals G2.
Oh, sorry. Yeah. Exactly. G equals G1 equals G2. So I think so. This is one of the interesting point to connect the theory of tensor categories and these non-local games. So we define this algebra as something governing the quantum isomorphism game, or more like quantum automorphism game, but it ends up having a Hopf algebra structure. That means again you have a coproduct. And co-unit. Satisfying the consistency condition of Hopf algebras that I will spare you the details. But anyhow, the upshot is this represents something like the function of algebras on a group, but not quite, because it's going to be non-commutative in general. But then the coproduct represents something like group row of the underlying space. Co-unit represents something like the unit element in the underlying space. Yeah. So, and for example, there's going to be antipode that corresponds to taking inverse. And that loosely explains why we can have something like inverse of quantum automorphisms, at least. I mean, again, if you look at the defining condition of antipode, I mean, you can get this co-unit, the unit element, as composite of the antipode and coproduct and product operation. And yeah, I mean, each individual factors don't make sense as star homomorphisms, but overall you get this very quick, easy star homomorphism. And the lack of sort of multiplicative property for the intermediate factors correspond to something like inverse of quantum automorphism, not quite given by inverse map. But anyhow, and then to check the consistency condition, or more like to check the existence of antipode, boils down to the theta twiddle being unitary isomorphism of Hilbert modules. And to check this quantum groups condition, I mean, if you just give coproduct and co-unit, this is a bi-algebra that corresponds to something like semi-group. And if you want invertibility of the group row, then you need to check something like equality of this form. That I guess you can interpret as having enough matrix coefficients for possible inverses. And yeah, so this boils down to understanding Hilbert module structure. And anyhow, I guess I better wrap it up. And if you are interested in technology behind this, I guess we do it later in the week. Okay, yeah, thank you for your attention. Quick question.
So in the paper by Mr. Richard Bertol, you have this idea of a quantum function.
Yeah. So the way so this this ambient system C really corresponds to their idea of quantum maps. I mean, so they work with sort of, in a way, they want to work with genuine tensor categories. So they end up working with something like H tensor B1 to B2 tensor H, or maybe I guess the reverse. So they want to work with linear maps like this, but that you can turn into linear map with this form, and their consistency condition for quantum maps exactly corresponds to this being a homomorphism. Yeah, and invertibility corresponds to like quantum isomorphism condition. But of course, then to have a genuine tensor category, you want to say H is in the same category as BIs, then finite dimensional Hilbert spaces then. But then you end up getting finite dimensional algebras here. So that maybe you want to avoid for general claim like this. Yeah.
So Mr. Reuter-Verdon, they also seem to work in a dual framework, so it would be their maps are star co-homomorphism. So it would be from B1 tensor H into.
Yeah, so this one maybe, so in the end, you.
So are they just working with beta tilde star?
Yeah, maybe a good point, but in the end, so I think you can resolve that mostly by taking adjoints, I think. And so the quantum isomorphisms is sort of symmetric under taking adjoints. So that's genuine. There's a genuine correspondence, I think. Yeah.
Maybe let me just ask one thing, because you're careful about talking about star algebra.
Yeah.
So does it have a universal system?
Yes, yeah. So that you can, I mean, so in the end, again, so I think formally you have to use this kind of characterization. So theCij's come from unitary Hilbert module maps. So there's a usual boundedness argument.
Do you just get the sort of pre-existing definition, namely the quantum automorphism group at the end line C-star algebra
Yeah.
that happens, then you throw in commutation with the adjacency?
Yeah. Yes, yeah. So actually, so for this one, in the end, it's going to be equivalent to the definition I gave. But then, so now there's an argument in Matthew's note, actually. After knowing that you have a quantum group structure, you can use a bit of structure theorem for quantum groups and really have the equivalence of two conditions. But yeah, so this one, yeah. So you really need to use this if you want to compare two definitions, I think.
If on the universal level,
Yeah. Yeah.
But can't you say that they're just the same for every action?
Yeah. So yeah, afterwards, yes, yeah.
Any more questions or comments? No, then thanks.
Yeah, thank you very much.